Hello, and welcome back to the second lesson of our Chapter 6 unit. This is Lesson 6.3, where we're going to look at additional properties of the binomial distribution. We'll talk about graphs a little bit, we'll talk about expected value, and we'll talk about standard deviation. So let's get started. So firstly, I want you to just think about, in these situations, what would you expect? So suppose you flip a fair coin 10 times. How many times do you expect the coin to land on heads? Well, probably you would expect, since we have a 50% chance of landing on heads each time, 50% of 10 flips is 5. So I would expect to land on heads about 5 times. Obviously, we don't expect it to be perfect, but that would be kind of our general expectation. Suppose you roll a fair 6-sided die 60 times. How many times do you expect the die to land on 6? So a fair die should land on each side about the same number of times. So if I were to roll 60 times, I would expect about 10 on each side. So 10 should land on a 6, about. And then lastly, suppose you take a 5-question quiz where each question has 5 answer choices. If you guess on every question, how many questions do you expect to get right? Now, this is a little trickier to think about, but if each question I have a 1 in 5 chance of getting the right answer because I have 5 answer choices. So if I answer 5 questions total, I would probably expect to get 1 right, 1 in 5. So where all of those, we did something we call the expected value. So we can find the expected value, otherwise known as the mean of a binomial distribution, by using the following formula. So this is our symbol for mean. It's called mu. It's a Greek letter. It kind of looks like a U, but it's got a little extra long thing on the front. We find that mean by doing n times p. Remember, n is your total number of trials, and p is the probability of success, the probability that that thing happens. So if we were to repeat this experiment many, many, many times, that number, that average, or that expected value, represents the average number of successes for all of those experiments. So if I were to take a whole bunch of quizzes that each had 5 questions, where I each had a 1 in 5 chance of getting a question right, over all of those quizzes, I would expect, on average, to get 1 question right per quiz, etc. So let's look at some examples. So suppose that 12% of M&Ms are red, which I got from the internet, so it must be true. If we choose 10 M&Ms at random, how many do we expect to be red? So one thing is to know, when you were asked this question, how many do you expect? We need to interpret that as they're asking for the mean. So our formula for mean, or expected value, mu equals n times p. In this problem, n is 10, because that's how many M&Ms we're going to take, and p is 12%, or 0.12. So I'm going to do 10 times 0.12, which is 1.2. Now, obviously, in a real life situation, we can't have 1.2 M&Ms that are red, but keep in mind this is an average. So we're always going to keep it as a decimal. Don't round it to a whole number unless you're asked to, because this is representing an average of how many red M&Ms we would get per group of 10 if we were to do this over and over and over and over again. So keep it as the decimal, even though it feels unrealistic. If we choose 100 M&Ms at random, what's the mean for the number of red M&Ms you would get? So same question, I just kind of worded it a different way. Expected value and mean are the same thing. So again, there's our formula. This time n is 100 because we're choosing 100 M&Ms, but p is still 12% because we're still talking about red M&Ms. So 100 times 0.12, which is 12. So if I choose 100 M&Ms, I would expect 12 of them to be red. And then lastly, a bag of M&Ms has approximately 210 M&Ms in it. What is the average number of red M&Ms per bag? So same kind of question. I just asked it in a slightly different way. My n is now 210. So 210 times 0.12 is 25.2. So in a bag of M&Ms, I would expect about 25.2 of them to be red on average. Again, we're keeping it as a decimal unless you are asked specifically to round it to a whole number. We want to keep it as a decimal because it's more accurate that way. So next thing we're going to look at is graphs. So we're still talking about expected value because this is going to kind of show up on our graphs. So let's say you flip a coin 10 times. Okay. Flip a coin. Coin has about a 50-50 chance, or 0.5 chance, of flipping heads or tails. And I want to know how many times I would expect to flip heads. So again, I use my formula, mu equals n times p. N is 10 because we're flipping it 10 times. P is 0.5 because the probability of flipping heads is 0.5. So that would give me 5. Right? What the graph of that distribution looks like is something like this. So the graph is showing us how many times we could flip heads if we were to continuously flip batches of 10 coins at a time and see how many were heads. So if I were to repeat that process of flipping 10 coins bunches and bunches and bunches of times, and each time count how many times I flipped heads, I would get this kind of graph that looks like this. So my expected value or mean is 5, and I can see that the tallest bar of this graph is happening at about 5, which basically means most of the time I should be flipping around 5 coins. Right? But that's not always going to happen. When I flip 10 coins, I'm not always going to get exactly 5 heads. So this graph is showing us like how often am I going to get 4 heads, how often am I going to get 3 heads, etc. And we can see that this graph looks pretty symmetric. Right? It's symmetric. It's got one nice little kind of peak in the middle. So it's a really good looking graph. Right? But what's if we had a coin that was unfair? Let's say a coin was unfair and only lands on heads 20% of the time. How many times or how many heads would we expect then? So same idea, but now my P is 20% or 0.2. So N times P, N is 10. We're still flipping it 10 times. 0.2 would give me 2. So on average, I should be getting about 2 heads per group of 10 flips. If I graph that, I can now see my tallest bar is on 2, but now I can also see that my graph is no longer symmetric. It's now kind of skewed to the right. And part of the reason for that is like the least amount of times we can flip heads is 0 out of 10. So it can't go any further than that. So we're kind of blocked at the lower end here, which makes our probabilities kind of start to stretch out in the other direction. So this one is a little bit more skewed to the right. But let's say we have another unfair coin that lands on heads 90% of the time. How many heads would we expect in 10 flips? So again, 10 is our N, 0.9 is our P this time, so 10 times 0.9, which is 9. And then this is what my graph looks like in this situation. Again, my tallest bar happens at 9 because that is our mean or our expected value. That should happen the most often. But my graph is now not symmetric, and this time it looks a little bit more skewed to the left. Again, we're blocked at the upper end. The highest amount of heads we can get in 10 flips is 10. So I don't have any further to go on that side. So that causes my bars and my probability distribution to kind of stretch out on the other end. So we end up with this graph that's skewed to the left. So that leads us to a little bit of a rule. So generally, smaller values of P, meaning values of P that are less than 0.5, are more likely to have graphs that are skewed to the right. And larger values of P, meaning values of P that are greater than 0.5, are more likely to have graphs that are skewed to the left. So below are the graphs of 3 binomial distributions. All of them have the same trial size, the same N, and I want you to match the graphs of the following, or match the graphs to the following values of P. So we have 0.55, 0.12, and 0.86. So starting with 0.55, it's a little bit higher than 0.5, right? So it's a little bit on the higher end, but not by much. So this should be a graph that looks pretty close to symmetric. Maybe not perfect, maybe a little bit skewed one way or the other, but it should be very, very close to symmetric. So I'm thinking that one's going to go to that middle graph. 0.12 is very, very small, and 0.12 is a very, very low number. It's a low value of P. And smaller values of P are more likely to have graphs that are skewed to the right, which means it would probably be matched this one on the left side, the first graph. So not only is it going to be skewed to the right, but remember, if we have a low value of P, then my tallest bar on my histogram should be kind of on the lower end. It's on the left. So skewed right, and then 0.86 is a higher value of P, so it's going to probably have a graph that's skewed left. And again, my tallest bar should probably be closer to the higher end of successes. And that's matching there. And again, if it's close to 0.5 in the middle, it should be roughly symmetric. And my tallest bar should be kind of in the middle of all of the other ones. So that's kind of our general rule, right? Low values, high values, skewed left, skewed right. But low and high values of p can have graphs that are symmetric if our sample size or trial size is large enough. So our rule here, and this comes from statisticians doing lots and lots and lots of trial and error, is that if n times p, which is the mean formula, if n times p is greater than 10, then the graph of the binomial model should look roughly symmetric. Again, maybe not perfectly symmetric, but roughly symmetric. So if I look at the graphs below, both of them have the same p of 0.10, which is pretty low. But one of them has a sample size of 12, while the other one has a sample size of 120. And I want you to think about which is which, right? So again, if we use our rule up here, that if n times p is greater than 10, then we know that the graph should look pretty symmetric. So if I think about which one of these, a sample size of 120 or a sample size of 12, is going to have n times p is greater than 10. So with 12 times 0.10 is 1.2, sorry. 1.2 is definitely not bigger than 10. So that one would not have a symmetric graph, which means our old rule applies. This is a small p-value. It should be skewed to the right, and it should have the tallest bar pretty close to the lower end of successes because the p-value is so small. So that's probably going to be this one on the right. Whereas a sample size of 120, if I use this little formula, 120 times 0.10 is 12, which is greater than 10, which means the graph should look roughly symmetric. But our tallest bar is still going to be kind of on the lower end of successes because p is still pretty low. So that's what happens with this one. We can kind of see that all of our bars on our graph got a lot narrower, and that squished the graph in so that we still have that kind of symmetric shape that we see. As opposed to this one, which had a much smaller trial size and things are a little bit more spread out. So that's kind of the comparison there. So let's do a couple of examples where we put those rules into practice. So let's say that a teacher has a large box with hundreds of expo dry erase markers in her classroom. Very realistic teacher scenario. And she knows that 28% of them are dried out and no longer work. I don't know how she knows that, but she's magical and knows that. So suppose the teacher picks out 5 markers at random. So her trial size is 5. Which of the following graphs is most likely to represent the model for the number of dried out markers she gets? Right? So my p-value, 0.28, we have to think about, is that low or high? Because that would tell me potentially, is it going to be skewed right or skewed left? Right? We can also think about that rule we just talked about, n times p. Well, 5 times 0.28 is probably not greater than 10. So probably that rule won't apply. And since 0.28 is a pretty low value of p, I'm guessing that this will be skewed to the right. So the one that matches it is this one over here, right? My tallest bar should be in the lower end of successes because p-value is pretty low, and it is skewed to the right, right? And our sample size n, 5, is not big enough to make n times p greater than 10 and make it symmetric. So it is going to be a little bit skewed. Suppose the teacher picks out 36 markers at random. So now my trial size is 36. Which of the following graphs is most likely to represent the model for the number of dried out markers she gets? So this time, I still have the p-value of 0.28. So I still know that my tallest bar should be kind of on the lower end of successes. So I can probably cancel out this right graph over here because that has a tallest bar that's in really, really high number of successes. So that's probably not it. So then the question is this graph going to come out skewed to the right a little bit, like this one in the middle, or is it going to be symmetric like the one on the left? And that's where we can pull out our little n times p trick. So if I do n times p, so n is 36 times p is 0.28, I get a value of 10.08. Which, even though it's close, is technically greater than 10. So that tells me the graph for this situation, for this model, should look roughly symmetric. So our correct graph is probably going to be this one on the left. Again, this is not a foolproof method, but it does help us to narrow things down and get somewhat of an idea of what a graph may look like. So let's talk about our last topic for today, which is standard deviation, and then we'll do an example where we put it all together. So standard deviation, we can find the standard deviation of a binomial distribution by using the following formula. So the symbol we use for standard deviation, it kind of looks like an O, but it's got this little extra little piece. This is sigma. It's another Greek letter. The way we find that standard deviation for a binomial model is by doing the square root of n times p times 1 minus p. And what this number represents, if we were to repeat this experiment many times, this number represents how far away each number of successes, each possible number of successes, is from the mean or the expected value. But I also like to think of this, and I put this in the notes if you're filling out the notes, I always like to think of this as kind of the give or take, right? It's the give or take for our expected value. So if our expected value is 10, the standard deviation represents, I expect to get 10, give or take a certain amount. So it's telling us how spread out are these values. It's not always going to be perfect. So this tells me kind of how spread out those values might be. So let's look at an example. We'll start with the M&Ms one because, apparently when I was writing these notes, I was thinking about M&Ms. So here you go. Suppose that 12% of M&Ms are red. We said that before. If we choose 50 M&Ms at random, what are the mean and standard deviation for the number of red M&Ms I would get out of the 50? So going back to my mean or expected value formula, so mean is n times p, so 50 times 0.12, which is 6. So in that group of 50 M&Ms, I would expect 6 of them-ish to be red. Our standard deviation formula is square root of n times p times 1 minus p. So if I plug in my values, n is 50, p is 0.12, 1 minus p, 1 minus 0.12 would be 0.88. So square root of 50 times 0.12 times 0.88 comes out to 2.3 in my calculator. So this is the standard deviation. So the way I might think of this is, okay, out of 50 M&Ms, I expect to get about 6 red ones, give or take 2.3. Right, so I may not always get 6. It would be pretty common for me to get something as low as 4-ish or 3.7 or as high as 8.3. Like that's still pretty common. So think of that as your give or take. So what that standard deviation represents, right? If we can expect 6 red M&Ms on average out of 50, 2.3 is the give or take how far our number may be away from the mean typically. Can we still get something less than, 3.7? Sure. We can still get something like less than 3-ish M&Ms. That can still happen, but it's less and less likely the further we get away from 6. Okay, so one more down here with the practice. Suppose that 23% of M&Ms are orange. A bag of M&Ms has 210 M&Ms in it. What are the mean and standard deviation for the number of orange M&Ms in the bag? So I went with orange this time. There are actually many more orange M&Ms than red M&Ms in bags of M&Ms, which is interesting. So the mean formula, so mean is n times p. N here would be 210 because we have 210 M&Ms in the bag, times 0.23 for orange. Probability is 48.3. Remember, we don't round unless we are asked to round to a whole number. Otherwise, it's good to keep it as a decimal because it's more accurate that way. Our standard deviation formula is square root of n times p times 1 minus p. So n is 210, p is 0.23 because that's how many were orange or what percent were orange. And then 1 minus p, so 1 minus 0.23 is 0.77. We put that in our calculator, square root of 210 times 0.23 times 0.77, we get 6.1. So in a bag of M&Ms, I would expect to get around 48.3 orange ones, give or take 6.1. So anywhere between like 42-ish and, I can do math the other way, 54-ish orange M&Ms is typical. Last example, again, putting it all together. A statistics test has 50 multiple choice questions, each with 4 answer choices. So keep in mind, if there are 4 answer choices on a question, my probability of getting a question right is 1 out of 4 or 25%. One of the students did not study and is randomly guessing on every question. What are the mean and standard deviation for the number of questions that the student would get correct? So first thing is to identify kind of what N and P are, because we're going to need that in order to use any of the formulas that we have. So N would be 50, because we have 50 questions on this quiz or test. And then P, like I mentioned, is 1 out of 4, because there's 4 answer choices. So 1 out of 4 or 0.25. So you have a 1 out of 4 chance of getting any question right, which is 0.25. So now we can use our formulas for mean and standard deviation and just plug in those values of N and P. So for mean, it's N times P. So 50 is N times 0.25 is P, which comes out to 12.5. And then standard deviation, square root of N times P times 1 minus P. So square root of 50 times 0.25 times 0.75 comes out to 3.1. So on average, we could expect the student to get about 12 and a half questions right, give or take 3.1. Right, so anywhere between like 9-ish and like 15-ish is typical to get correct out of 50, which is not a very good grade, by the way. So I do not recommend guessing on every question. You should study. What would the shape be for the probability distribution describing the number of questions? So just thinking about shape and using our rules for shape, right? We said if our P is on the lower end, which it is, it might be skewed to the right. So P is pretty small, so maybe it's skewed right. But then I have to think about, well, remember there's that little rule where if N times P is greater than 50, or I'm sorry, greater than 10, then we can say that our graph looks roughly symmetric. And N times P is basically our formula for mean. So I know N times P is 12.5, and that is bigger than 10, which means that our graph should look roughly symmetric since that number is greater than 10. Basically, this means our sample size is big enough that it's going to make all of those histogram bars kind of squished in, and it'll give me a nice little symmetric shape, even though our p-value is so low. So that is it for this lesson. I'll see you guys in class.